Assalamualaikum warahmatullahi wabarakatuh. Today we will be presenting our design project report entitled Stability and Deformation Analysis of a Segmental Retaining Wall using PLAXIS. So here is the overview of our presentation today. Start with introduction, summary, modeling approach, results, discussion and reflection. Now we will proceed to the introduction. Segmental retaining walls, SRWs, are commonly used for grade separation in roads, rail embankment, and commercial projects. SRWs are popular due to their quick construction, modular design, and cost effectiveness. The performance of SRWs relies on the combined action of three main components: the wall face, the reinforced soil mass, and the foundation. If any of these components are inadequately evaluated, it can lead to failures, highlighting the importance of thorough stability and deformation tests. To improve performance, SRWs are often reinforced with geogrids like Miragrid. These geogrids help enhance internal stability and reduce outward deformation or bulging of the wall face. In Malaysia, SRW design is typically done using limit equilibrium programs such as RisiWall or SRWall. However, these methods do not account for complex interactions like differential settlements and stress concentrations. To address this limitation, finite element method analysis using software like PLAXIS 2D or 3D provides a more detailed view of soil structure interaction. This analysis is increasingly used for verifying design in transportation infrastructure projects, as it can measure global stability, horizontal deflection, and settlement.
So this is our summary for design project. First, for foundation soil, we use clearly sand, and then for our base soil we use well graded gravel, and for our drainage layer we use poorly graded gravel. And then for our geometry for our design project, for the wall geometry, total wall weight was 5.63 meter and the surcharge load was 10 kilopascal. For our SRW unit details, we use unit weight, unit height of 0.15 meter. Our initial shear capacity was 13.7 kilonewton per meter, and our maximum shear capacity that we got was 89.0 kilonewton meter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Zulfikri bin Saiful Bahari, and now I will present the modeling approach for our model. So for the modeling approach, we use PLAXIS 2D model and created following the RisiWall design under plane strain conditions. It included all soil strata, facing elements, and geogrid reinforcements. The construction sequence was simulated step by step to accurately represent real site conditions. So for the material models, for soil is more column model, SRW facing, elastic model, and the geogrid is PLAXIS geogrid element. So next is the input parameters for PLAXIS. So first is the soil properties for backfill soil. Then here we have the foundation soil. So here we have the segmented retaining wall, SRW. And last but not least is the reinforcement or geogrid.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Firdausain bin Mustafa Kamal. So this is our deform mesh results with the maximum value of 5.646 power of -3. Next is displacement contours. The total displacement scale up to 500 times. So the maximum value is 0.05697, the power of -3, and the minimum value is -2.071, the power of -3 meters. Then we can see the vertical settlement for our displacement contours. Next is factor of safety. So this is the results of deformed mesh with annotation of factor of safety value. We can see the factor of safety curve with the highest MSF value is 2.138.
Okay, for the discussion part, the PLAXIS 2D analysis shows that the segmental retaining wall achieved a factor of safety of 2.138. However, localized issues were identified that may affect the long-term serviceability. The key failure mechanism observed include the bulging in the upper wall, high reinforcement strain in the mid to upper geogrid layers, base sliding tendency, and the deep soil displacement. Okay, to address these failure mechanisms, several design improvements are recommended. So some of it is upgrade to stronger geogrids and reduce spacing for better load distribution. Use mechanical connectors to improve block to grid interaction and resist bulging. Add a shear key to roughen base layer to improve slide resistance. Enhancing drainage with a granular blanket or perforated pipes to prevent saturation. And lastly is to implement long-term monitoring using embedded strain gauges to detect early deformation.
So this is our critical reflection for our project. First, we have strengths in wall design. Second, we have gaps and limitation. And lastly, we have potential improvement. So for strength, height safety factor are achieved for all major failure modes. For gaps and limitation, embedment depth is only 0.15 meter. Be sufficient for erosion prone or weak subgrids. So for potential improvement, we need to provide a functional back drainage system for slope.